Guys, what grade are we in? 11. Let's start acting like it. So that means Damon. Yeah, you. The people around you as well. Just ask for quiet and listening. You start talking about a watch. Like, come on. Thanks, guys. So, once this lesson's over, I'll take this recording and I'll put it up on the OneNote. This is also, you're looking at the OneNote right now. If you haven't seen already, I've been putting the topics we've been going through in the Unit 1 stuff. There's the PowerPoints and the handouts I've been giving you. I haven't put the sheets, like the question sheets up there, but I thought about it. I'll start doing that as well. So you have them there for later reference. We didn't get to this one the other day because the images on my PowerPoint failed. So I quickly want to go through this one, guys. If I was to say to you, what is the boiling and melting point of that substance? Hands up if you reckon you could find those two values from our graph. Cody can. Abel. Yeah. Jack. Campbell. Yeah. Damon, you reckon?
Yeah, I reckon.
Wade, do you want to have a crack at it? Cody, do you want to have a crack at it?
Obvious. I can't. Yeah, that's what I was going to say. Because that is on my speech.
Should have said it then. You would have got all the credit. Instead, Cody gets it all. So we've got melting points. We've got melting point at 60, boiling point at 120. What does this section of my graph here, what does that represent happening?
ML. Which part? ML. It's beautiful.
No.
Yeah.
This section here, yeah, it's to do with the heat capacity. So heat is being put into, or heat energy is being put into this, whatever it is, substance. So we're putting direct heat into it, but it gets to 60 degrees and we keep putting heat into it, but the temperature doesn't rise. The temperature, even though we put an extra 20 kJ of heat into it, extra 20,000 kilojoules into it, it hasn't turned into a liquid yet. Because that there, this here, that is the latent heat of fusion. And for this one, what is the latent heat of fusion for it? That's the temperature that its melting point is, but that's not the... Yeah, it'd be 20 kilojoules. So once you get that material to its melting point, freezing point, you need to put in an extra 20 kilojoules to bump it up to the next state of matter, or to bring it down to the solid, and which way you're going. Does that make sense, guys?
Yeah.
Don't ask me how long I spent on this, but I had the thought to myself, well, is the latent heat of fusion for this, is it 30 because that's the point that it goes up, or is it 20 because that's how much energy you need to put into it? And the fun thing about being one of the only two physics teachers here and not being experienced in it, and the textbook is being a bit dodgy, is it was very hard to find that answer. So the latent heat of fusion is this flat line, how long that flat line is basically, because that represents the extra energy you need to put in to turn that substance into its next state.
Like, you reckon the textbook is very good?
It doesn't have answers in it, which is trash. I've gone on at length about how trash that is. But as well, sometimes Like, there's questions like this in your review section, but they haven't given you examples of this in the actual work solution section. What is the latent heat of... What's LV, latent heat of vaporization? 30?
Intentional stuff.
No, not today. Yeah, so it gets to its boiling temperature at 120 degrees.
Oh my god.
Okay. 30 kJs is the latent heat of vaporization. Now, the question B, it says calculate the specific heat of the substance. Where would we look for the specific heat of this substance? Which sections of the graph would we find the specific heat? Sam? No.
Specific heat of what?
That's a good point. It does change. The question is asked to find the specific heat. The specific heat of it when it's a solid and a liquid look pretty similar. But can you see that this... Because what I mean by specific heat, guys, does anyone remember the definition of specific heat?
And by 1 degree.
To change 1 kilo by 1 degree. So can you see here, I've put 10 kilojoules into it, and I've gone up by 20 degrees. Up here, I've put 20 kilojoules into it and gone up 20 degrees. So the specific heat of the gas is definitely lower. You look here, we've put 20 kilojoules into it, gone up 60. So, oh no, that one's different too. So, let's find, and it's got over on the left there that it weighs 1.5 kilos. Oh, that was the wrong button to press. There we go. So I want to find the specific heat. So, let's do as a solid first. What's my formula when we're working with specific heat? Q equals MCAT, or MC delta T if you want to be correct about it. Do we know Q? Because we're looking at the solid state at the moment. Do we know how much energy? Yeah, we put 10 kilojoules into it. So I'm just going to put my variables down the side. So Q is 10. Are we in the right units? We're in kilojoules. What does the subscript K mean? Yeah, it's times 10 to the 3 or 1,000. So times 1,000. So we actually have 10,000 joules. What's my mass? Do people other than Cody know this as well? Okay, good. Yeah. Do we know my specific heat capacity? That's what we're figuring out, so we'll leave that as a question mark. And delta T. It's gone from 40 to 60 degrees. Delta T is 20 degrees centigrade. So my function becomes... And this is a point of personal preference, guys. I said this the other day. I'll say it again. I prefer to rearrange my formulas when they're all letters, because it's a bit less messy. Some people prefer to sub in and then rearrange. It's up to you. I don't care. Both ways are correct. This is the way that I personally prefer, but I understand not everyone else does it this way. So I'm going to start with my rule, Q equals MC delta T, and I want to find my C because I have these other values. So I want to get C isolated from the other variables. I'm just going to divide through by everything else on the same side as it, because they're all attached with a multiplier, so I can divide to get rid of them.
And this is only for the specific key as solids.
This is only for the solid. We're going to get different ones for the other ones. So that gives me the rule C equals Q over M delta T. I'm going to chuck it in brackets now because you're going to want to do that later anyway to make sure you get the right answer. Why do we have to put brackets around it?
Otherwise, it'll be the
because when you put it into your calculator, you will get the wrong answer if you don't. Because there's two things on the bottom of the fraction, they need to be solved before you do the operate on the fraction. Which gives us C equals 10,000 divided by 1.5 times 20. Lachlan, can you solve that for me? I mean, everyone else as well. Specifically, I want the answer for it.
plenty of time.
What one is an energy source that provides 1 joule of SA? That means to be now.
Yeah, so yeah.
I'm going to go through those numbers.
Very.
Oh, the announcement.
Good afternoon. We are still looking for Mr. T, Math Year 9. Scene 5. We're looking for Mr. T's class. DNT. Could you please open?
Discovery point for it. Pretty tomorrow. Soon. It's done. That's what we're going on.
Times 2. Yeah, no, 20. Because it's 20 degrees. By the way, guys, the answer we got is 3.33333333. That's not. What would I round to?
3 point.
About 6.
3.
Well, what's our 3? Think back to the very first lesson we did. How do we decide how to round to?
Just round up the whole.
Jack.
The
Lowest amount of significant figures. If I cast my eyes to this, the lowest number of significant figures would be those 2 significant figures. So where's significant? So we've got this one. Well, this one we've got 1, 2, 3, 4, 5. This one we've got 1, 2. This one we've got 2 as well. So 2. So we're going to round to 2 significant figures. So we go 330. Are you wondering why is that 2 and not 1? No? What are you wondering?
Okay.
Okay. What's my unit for C?
Kilos. No,
Kilos is in it. It is joules per kilo per degree Celsius.
You think Kelvin is?
That mean the same thing in this context.
So, I started with it, kilos. I mean, I started with Kelvin. Now this.
Okay.
It's 330.
Sorry?
330.
330. Because the answer in the calculator would be 333.333, etc. But in physics, we round to the lowest number of significant figures, which for us in our things here is 2.
So that 3 means that in the first place is so 0 and 3 days. Nice.
The 0, we've rounded it off to 2 numbers, 2 significant figures. Because the number that we cut off was a 3, we've rounded down to 0. If it was 337, we would have rounded up to 340.
Yeah.
Okay, now, what I'm going to do, front 2 rows, you're going to find me the specific heat capacity of this object or this material as a liquid. Back 3 rows. You're going to find me at a gap. Yes.
My parents are involved. I worked at
At the gap. Yes.
I don't know. Or except for the mutual. Yeah. They stop.
No. Can you see? This is basically, from here to here, it's still a liquid, but once the line, it's okay, now it's changed over, and our heat energy that we're pumping into it has gone back to just raising the temperature instead of changing the state. Yeah.
Specifically. Yeah. Okay, because there's no short for yes. Try you that
Considering I just asked you to do this one, let's get cracking.
no, curious. Tell the
You just have to quietly inferred Q as delta T buffer. Okay, you should be almost in that line. There. Speaking without concern.
I get this age in life. Yeah, because we're from that one with the stress. Oh, I see. Specifically,
Yeah. What I did, and what I did for that, I'm one. Why do it with a one? Yes.
It's going up. So let's look at the activity. So the kilo one.
I probably have it on my desk. Sorry, let's think about one as quickly. So it's put in 10,000 Celsius to get it to heat. Then you put in a bunch more energy, but the temperature hasn't risen, because that's to get it to pump in enough energy.
I got it now.
Yeah. So it's got, at this point here, it has 30 kilojoules of energy in this material. And then you kept on putting energy into it, you put another 20 into it to get 50 total.
At the end,
That extra 20 has made the temperature go up to 60. So your Q, the energy input into the system started at 30 and 60. So you put 20. Yeah, yes.
Because if you can't 30 and 50 bring in 20 kilojoules of energy,
Okay, I think we're starting to have a few people done.
Oh, what's this? 2-0. Well, we got 4.5. What is energy? What is? What's that? You should say. Okay. So if you look along, you can get it into a graph. Take this as wet. Yeah. I don't know. You guys also prevent it. That's what. After what they already do. Oh, yeah. Yeah. What kind of things? I'll give it all. I wrong. Oh, it's kind of it. Well, like also the power in that time. Sure. Maybe feeling that. Oh, you're on this next solo. Yeah, I need that. If you need to one more back, Let's move on. There's another and then that's better way, and then there's like another big what's our so when that's what you and this well get your own and just see it I like turn it out exactly right now and then it less than so like you can get focused you use see that feel like that's one thing I told that
Okay, guys, eyes on me. Mouth shut. Listen up. Eyes on me. Mouth shut, please.
Alright. Nice.
Eyes on me. Eyes on the angular con. Okay. Going around, it looks like people are starting to get this. For our liquid group, what was our specific heat capacity C that we found?
We got two.
You got
220.
220 kilojoules. Joules per kilogram per degree. Cool. And up the back, what did you get for your one? 670 joules per kilo per degree. Okay. I want you guys, this is the sheet I gave out as homework the other day. I'm going to zoom in here. I'm going to do this here. What I want... This is very similar to what we've just done, guys. The only difference is, this time we have time in seconds as our x-axis. There is something I haven't been through with you yet that will help you understand this. And that is, if you read the question, it says, it shows the relationship between the temperature of 100 grams of an unknown substance and the time it is heated by a 1,000-watt source. Because I'm not normally a physics teacher, I had to go look up exactly what a watt relates to. You know, I've heard of like 50-watt bulbs or whatever. But a watt is 1 joule per second. A watt is 1 joule per second. So how much heat energy is that 1,000-watt source putting into our object every second? So you can pretty much, if we know it's been there for 20 seconds, how many joules is that?
No.
Thousands.
Oh.
If it's been there for 150, how many joules is that? 150,000. if we have not already had a crack at that question, guys, can I get you to have a go now? At that question 6. If you have finished that, can I get you to go down here to your textbook questions?
Always around to the smallest amount. See?
Okay. Before we go off on that though, guys, eyes up on me. Who just has question 6 to go? Okay. Who's ready to have a crack at? Oh, I don't think anyone's ready to go up there. But once you do question 6, I will give you maybe 5 minutes to do it, and then I'm going to come up and do it up here, and then I'll get everyone to have a go at this. So I'll leave the recording going till actually I can pause it, can't I? Okay, so I'm recording again, guys. Let's have a look at this one. We'll answer question 6 together. So, what is the melting point of the substance? The melting point is just where it swaps from being a solid to a liquid, which will be 80 degrees. So 80 degrees Celsius. What is the boiling point? Well, that'll be where it swaps from a liquid to a gas. Should be 150. 150 degrees Celsius. How much energy is required to melt the substance? Where did you get 180,000 from?
Added 8 times mass, negative 90.
So what you found is Okay, I think what you found is the latent heat capacity. Okay. Yes. So guys, for those who didn't just catch that, Lachlan said, is it 130? And the answer is yes. Because what's another word for the amount of energy it requires to melt a substance? What's the scientific word we've been using to describe that? Latent heat of fusion. So it's just asking us how much energy does it take to go from here to here. That's the latent heat of fusion. Why? So that'd be 130. So it takes 130 seconds of that 1,000 watt source. So 130,000 joules. Looking around the room, guys, I appreciate that some people are on a slightly different spot, Abel Rock, but looking around, there was a lot of confused faces when I just went through this one. I need to know when people understand it, when they don't, because that lets me know what I need to practice more of with you guys. If you're doing your own thing, I don't want to find out in 4 weeks' time when it comes to your data test you don't actually understand this. The way you show me that you understand it is when we go through it and I look around and I see people going, that lets me know that we need to spend more time on this. But if you're doing your own thing, there's no way for me to know how the class is going. The reason the energy required to melt the substance is 130,000 joules is because we're just looking for the latent heat of fusion. That's how much energy it requires to melt or freeze a substance, depending on what direction you're going. To find the latent heat, we just need to find how much energy, once it reaches melting point, it takes to get to the next state. For us, it takes 130 seconds. We have a 1,000 watt heat source. That means 1,000 joules per second, so that means 130,000 joules. Okay. D, what is the latent heat of fusion of the substance? C above. 130,000 joules. Sorry?
Why not?
Because the latent heat of fusion is another way of saying the energy required to freeze. Because, and this is tricky, They want you to understand that connection. They want you to understand both ways you can be asked to find that. What is the specific latent heat of vaporization? C and D are the same answer, yes. Yep.
How can you melt steam and create it?
Because if you start with a solid at 80 degrees, how much energy, according to this graph, do you need to put into it for it to turn into a liquid? 130,000. If you start with a liquid, once again at 80 degrees, how much energy needs to be removed from the system to turn it into a solid? 130,000. It just depends whether you're putting it in or taking it out, essentially.
Yeah.
Next one, guys. Latent heat of vaporization. Lachlan? It'll be more than that, I think. Because if you look here, latent heat of vaporization is this. Sorry?
This should be pointing to that.
Yeah, and then so how many joules is that going to be if it takes 1,020 seconds?
Yeah. So it's
1 million. What a moment to have a brain freeze. Joules. Yes. I have one too many. Because this is 1,200. Yeah, that's a J. Sorry.
Yeah, one. Yeah. I just want to fire. I just don't feel like everybody fully understands.
No more confusion, Jack. Okay, I just want to repeat this, guys, because this is 100% going to come up again. If we read our question, it's being heated by 1,000 watt source.
What?
And a watt is 1 joule per second. 1,000 watts, I don't have that many fingers, would be 1,000 joules per second. So the number of watts is just how much energy it is. So we can show this as a time graph instead of just energy and temperature. We can instead show time and temperature if we know the watts. Yep.
So is it?
Yes. Which no, it would be 1,020,000. You don't believe me? Chuck me your calculator.
Oh.
It's just M times LA. M times LA. Oh. We've done a silly here, guys, and by we I mean me. Because okay, thanks guys. Can anyone see the mistake I've made? I've said the latent heat of fusion of this substance is 130,000 joules.
Yeah.
What is the definition of the latent heat of fusion?
The amount of temperature.
The amount of energy it required to get 1 kilo. What do we have? We times it by 10 essentially. But because our rule, so my rule, the energy required would be mass times latent heat of fusion. So for us, we're just gonna, we know the energy put in. Oh no, so we divide by 0.1. We divide by 0.1. Which is the same thing as timesing by 10, which will get you the same answer. So guys, this is our rule.
Yeah.
Yeah, I'm gonna. This is our rule, guys. Q equals LF, MLF. Yep. Okay. We know to turn this substance from a solid to a liquid, it took us 130,000 joules.
So to get L1, you have to divide by that.
We know that M, 0.1, 100 grams, 0.1 kilos. To get LF, divide by 0.1, divide by 0.1. The latent heat of fusion will be 1.3 million joules. Because, yeah, I completely forgot that we've got to take the mass into account.
And divided by 6.1. If we get it, and you got a big enough, we get to show you that questions and stuff.
Okay. If I times by 0.1, would the number be bigger or smaller? So when you divide, you would expect the opposite to happen.
Yeah.
It's the same way as if you times by 2, your number gets bigger. If you divide by 2, it gets smaller. When it's a number less than 1, it flips. Timesing makes it smaller, dividing makes it bigger. Yeah. Well, guess what, Abel? You learned something today. It's been a good day. Okay, we'll do the same thing for latent heat of vaporization, guys. Q equals MLV. What's my Q for how much energy did it take to turn my liquid into a gas?
Why?
That much.
So with the form of trade, so we get it out by getting the actual latent heat. Yes.
No. So you mean this? Oh, sorry. Do you mean question C? Yeah, C would stay the same because it's this particular substance, like this amount of it. So for this one, same things, guys. Divide by 0.1. Divide by 0.1. So my latent heat of vaporization is the same thing, but it'll be 10,200,000 joules. Well, aren't you lucky that you write down as you go? So if you ever forget, you just look back up at the line above. Okay. Guys, I'm